Well, hello there. Did you know that the richest 20% of the humans own 80% of the world income? Well, this follows the Pareto principle, which tells us that, as a rule of thumb, 20% of the causes are responsible for 80% of the outcomes. In 1896, Vilfredo Pareto showed that 80% of the land in Italy was owned by 20% of the population, and later many researchers found that this 80-20 imbalance appears a lot in the world, including natural phenomena and human activities. For example, in the US, 20% of the patients use 80% of the healthcare resources, and it makes sense, since chronically ill patients will use the services a lot more. Healthy people barely go to the doctor anyway. This is not a problem that is unique to the US. In Colombia, there is an organization called Omnivida that saw that severe asthma patients were using a lot of the healthcare system resources, and primarily they wanted to find a way to predict which patients will not follow the treatment in an adequate way, thus becoming non-adherent patients. So these patients will likely use the healthcare resources more often because they are not healing and failing to follow their specific treatment. So Omnivida reached out for help at the Data Science for All program, and we got really interested from the beginning because we saw an opportunity in that problem. If we fix 20% of what's wrong, we could potentially solve 80% of the problem. Additionally, what really got our attention was the fact that asthma is a respiratory related disease, just as COVID-19, and we wanted to reduce the load of resources drawn into that area. That would mean that if we can somehow reduce the amount of people that fail to follow the doctor's advice, less asthma patients will continue to be patients, freeing resources, breathers, medicine and doctors, and most importantly, improve those individuals' health and well-being overall. At this point, we thought that if we want to have a chance against COVID-19, we have to help as much as we can, and we will use your recently recharged data superpowers for good, because no one else will do it for us. We jumped right into the project, and the first thing we did was to contact with the company. We talked to them, and once we had a solid grasp of what they wanted, we took a look at the actual data, so we could ask ourselves the right questions. How can we identify patients that will most likely abandon the treatments? What are the most common trends and patterns that those patients follow? And most importantly, what actions can we take to diminish the non-adherence to severe asthma treatment? We started with 18 different CSV files, each with different kinds of information stored within. Then we quickly explored the data and decided to group the dataset into 5 categories, and kept one extra with the historical adherence data: patient demographic and humanistic data, clinical data, pharmacological data, external sources data. For the historical data, one of our first findings was that a stunning 68% of the patients had always remained adherent throughout all their treatment, and they always got high scores in each and every one of the quantitative adherence tests. Moreover, another 16.5% of the patients got good scores in most of the tests, but failed to pass some by a close margin. Finally, just 15.5% of the patients got predominantly bad results. So we decided to focus on that 32% of the patients that kept switching from adherent to non-adherent and vice versa, so that we could identify the factors that led the patients to fail the exams and become a non-adherent patients in that particular time they did. We counted the times each patient changes states, calling a negative transition when they went from adherent to non-adherent, and a positive transition otherwise. We did this to find out how much adherence changes over time, allowing us to keep track of the evolution of each patient. The main idea of this approach was to identify the effect of different variables from other datasets, using a reasonable time window for the points of interest, so that we could see any correlations. At first, we took a more in-depth look at the different datasets and found that Omnivida did a good job applying adherence surveys more consistently after 2017, Most of the patients were adult women who lived in Antiochia's urban areas belonging to the lower middle class, and almost all of them used omalizumab. In a lot less quantity, other medications were also used throughout the years. We could also see that most patients participated only once or not at all in well-being surveys, which were mostly implemented in 2017. On the other hand, the number of hospitalizations per patient shows that very few patients ended up going to the hospital over 20 times and by the same causes, clearly an example of this 20/80 rule. Finally, after having engineered the most prominent features, we built, trained, and evaluated 4 different models, one for each type of data. Then checked the importance of each feature in the models and implemented them. As a conclusion, we found that non-adherent patients with opportune well-being monitoring were more prone to make a positive transition than non-adherent patients with late or no well-being monitoring. Also, we found a clear relation between the timely supply of medicine and patient adherence. This was later confirmed after training the classifiers and seeing that the most relevant features were related to the amount of medications provided to the patient, how timely these medications provided, and if there were any issues preventing the patients from getting them. Lastly, one of the most challenging aspects of the project was dealing with highly diverse, unbalanced, and temporal sparse data. For example, patient-related records follow the progress of the patient throughout the time with no identifiable periodicity. So in order to have more robust results, it would be better to stick to a scheduled check-in plan instead. In order to mount it on a web page, we structure all the backend development in Python using the Flask framework, responsible for processing the requests from the users. The backend server lives in an Amazon instance, and it communicates with the database and the frontend. The front-end visual elements were developed using Vue.js, a JavaScript framework which uses the infrastructure in the backend to let the users interact with the platform through a web application hosting. Firebase Hosting Service was used as a web hosting service to deploy the frontend. It allows individuals to interact with the application through Firebase computers, which will then connect to the server and the dashboard, and the information will be delivered through the web browser. Our application displays 3 main sections: dashboard with some charts and informative widgets, patient information input form, and patient monitoring. The dashboard section presents some relevant data such as the average treatment, the adherence over time. Here we can see the number of adherent and non-adherent patients and how their condition evolves, and also how adherence is divided among demographic features such as age and gender. The next feature will be available in a future iteration of development. It's basically a form where people from Omnivida will be able to register new patients into the system and add their data. Implementing it proved to be really challenging, as the models needed a minimum of historical records to work properly. Lastly, in the patient monitoring section, people at Omnivida can check the adherence percentage of their patients one by one and could decide to take actions based on this information. Thank you all for watching until the end. This was the summary of our work as Team 22, and we hope that you enjoyed the video. See you and take care, everybody.